Thank you so much for that introduction. Thanks to the conference organizers, all the other speakers, all of you guys for being here. This has been a phenomenal few days, really, really special time. But I can't spend too much time talking about that because we've got a lot to get through, so let's go ahead and jump in. So here's a quote that was definitely actually said. You can't prove that I'm wrong. So here's some things about me. If you want to take a photo of this slide, you're welcome. I'm not going to spend too much time on it. So what is this talk about? I'm going to bury the lead just a little bit here, and we'll talk about it in a few slides. But first I want to talk about netstack 3. So netstack 3 is Fuchsia's next generation pure Rust networking stack, and it aims to replace netstack 2, which is written in Go. So I started netstack 3 about 6 years ago, led its development for the first 4 years, and then for the past 2 years it's been led by a different team. Now, I haven't been on the project for 2 years, so obviously this is beyond me now. It's a huge team effort. I'm going to be bragging a lot about those folks. There are some really good engineers who work on that now. Now, writing a networking stack is a very serious undertaking. It's responsible for almost all networking traffic in the operating system. It implements dozens of protocols, each of which is specified across hundreds of pages of documentation. And it is the first line of defense for any attacker who's trying to get into the system, other than the ones who are sitting physically in front of the device. It's also just big. As I said a second ago, it's taken us 6 years to get to this point. There have been, plus or minus 10 developers that whole time. It's split across 63 different crates that span a total of 192,000 lines of code. That's more code than the top 10 crates on crates.io combined. So over the past year, the team has finally been getting ready to actually launch. And those of you with networking backgrounds will know that you don't just deploy networking code into production, right? Networking code is famously difficult to test. And so you have to assume that despite all of your best efforts, your code is just riddled with bugs. And so for a project of this scale, deploying an entirely new ground-up rewrite of a networking stack, you would expect to dog food in the field for months or maybe even years before you actually ship to real users. And in that time, you would expect to uncover tens or hundreds of bugs that you hadn't seen during development. And only once you'd burned all of those down and seen relatively stable behavior for a while, then finally you're willing to actually deploy to real users. So let's talk about what that process has looked like for netstack 3. So for the past 11 months, the team has been ramping up a dogfooding program. It's at peak been about 60 devices running nearly 24/7 in developers' homes. And again, if this were any other netstack, we'd have expected to uncover a giant mountain of bugs in that time. So over the past year, how many bugs did the netstack 3 team uncover in the field? 3. So this talk is going to be something of a flashback, for those of you who might get the Emperor's New Groove reference. And I guess it's sort of weird that he's sad, so yeah, that's better. So netstack 3 was designed around a particular methodology for how to architect robust systems. Now, hopefully I've convinced you that we did at least something right on the robustness front. And in a sentence, that methodology says, buggy programs don't compile. Now, obviously, I am far from the first person to suggest this methodology. Here's just a small sample of crates that use this methodology somewhere in their API. And here's a small sample of what's been written on this topic, both about Rust and about other languages. So my goal for this talk is not to introduce a new idea, but instead my goals are, first, to propose a concrete but general framework that attempts to fully unify all of the different ways that this methodology shows up in practice and explains them in terms of the same basic fundaments. Second, I'm going to walk through 2 examples, one from the standard library and one from netstack 3, and show how we can explain those examples in terms of this framework. Now, unfortunately, 25 minutes is not enough time to go into more examples in the depth that I would like, and I had to leave a lot of examples on the cutting room floor when I was writing this talk, including the original research that I talked about in the abstract, so sorry about that. You're not going to hear about that. But I promise that these 2 examples, they only begin to scratch the surface of what is possible. I have a long list of references that I'll mention at the end, and for people who are interested, I really encourage you to go read them. I think that you'll be surprised by the diversity of different problems that this methodology has already been applied to, and I personally have many more examples from netstack 3 and from other projects, so please come talk to me if you're interested in those. So what exactly do we mean when we say that buggy programs don't compile? Well, on the website, Rust advertises 3 properties: performance, reliability, and productivity. So let's zoom in on reliability. The website says, and I'm quoting here, Rust's rich type system and ownership model guarantee memory safety and thread safety. In other words, out of the box, Rust guarantees that buggy programs don't compile, but only if we restrict our definition of bug to memory bugs or threading bugs. Now, don't get me wrong. Memory and thread safety are huge on their own. For example, netstack 3 is able to pull all sorts of crazy like buffer sharing tricks in the name of performance that would be wildly dangerous in C or C++. I actually gave a talk on some of those techniques at Rust Belt Rust in 2018, so if you're curious, there's a link in the references. But that's only half the story. Many critical bugs that we would like to prevent are neither memory bugs nor threading bugs. So let's take TCP as an example here. If you want to implement what RFC 4614 refers to as basic functionality for TCP, you need to implement 6 different standards that run a combined 270 pages. And if you add in the recommended enhancements, that number jumps to 18 standards and 476 pages. And that's just one protocol. You add in Ethernet, ARP, NDP, IPv4, IPv6, ICMP, IGMP, MLD, UDP, and a host of others, and all of the subtle interactions between them, and you can start to appreciate that maybe memory bugs and threading bugs are just the tip of the iceberg of all the fun and exciting ways that you can fuck it up. So that's why uncovering only 3 bugs in nearly a year of dogfooding is so surprising. There's just no way that memory or thread safety alone would get you to that level of robustness. So the points that I'm trying to make are 1, that out of the box, Rust guarantees that buggy programs don't compile only with respect to a small subset of the bugs that we actually care about. And that 2, netstack 3 would not have been able to achieve that level of robustness if it had only been relying on what's provided out of the box by the language. However, what netstack 3 has done, and what I believe that any project can do, is to extend the Rust language and guarantee freedom from almost any class of bugs. This is what I mean when I say X safety in the talk's abstract. So as it stands today, Rust provides some core set of abstractions, and it guarantees various safety properties related to those abstractions. This is just sort of a smattering example. But the majority of the abstractions in the ecosystem are provided by libraries. And generally, libraries don't provide the same degree of safety with respect to their abstractions that we might expect out of the language. But it doesn't have to be that way. As we'll see in the following examples, Rust's core abstractions on their own are enough to express almost any safety property that we might care about. My claim is that every library can and should provide the same level of safety with respect to their abstractions that we would normally expect out of the language. So let's get into this framework. To explain it, we're going to turn to the humble binary tree. Getting back to some CS 101. So in order for our binary tree to be correct, we of course need memory safety, obviously, but we need other safety properties as well. In this case, we have to ensure that the tree is ordered, right? That every value in the left subtree is less than the value in the node, and every value in the right subtree is greater than the value in the node. Now, Rust can obviously guarantee memory safety, but it has no visibility into this ordering requirement, and so it can't enforce it for us. So how do we make sure that we never produce an invalidly ordered tree? Well, we use the concept of an invariant, right? We document that there's some ordering invariant that has to hold for any node. We ensure that anytime we create a new node, we make sure to uphold that invariant. And finally, we ensure that every time we modify an existing node, we make sure that that invariant is still upheld, assuming that it was upheld to begin with. Now, imagine that you're writing code that is outside of this module. And here we're going to talk just about safe code. Obviously, unsafe code can do whatever it wants. My claim is that from the perspective of safe code outside of this module, there is no difference whatsoever between the safety invariants provided by the language and the ordering invariant provided by this module. If you write code, which, if you were to run it, would violate Rust's memory safety guarantees, then Rust's entire promise is that that code will not compile. But by a similar token, if you write code outside of this module, which, if it were to run, would violate this ordering invariant, then similarly, that code will not compile. In other words, by structuring our code in this way, we have, in some sense, taught Rust about a new safety property that it didn't know about before. So we can use this node example to explain the framework that I'm trying to propose. The first step is definition. We define an object which the Rust type system is able to reason about, so in this case, the node struct. We attach to this object a safety property which Rust cannot reason about, in this case, the ordering property. Now, because Rust can't reason about this property, it's on us as the authors of the abstraction to make sure that we actually uphold it. So the second step then is enforcement. In enforcement, we guarantee that the safety property is upheld, and that responsibility is on us as the programmers. So in this case, we use field privacy, right? We make sure that the actual fields of the struct are private, because if they weren't, code outside the module could go and invalidate our invariant. And then we make sure that all of the code that we write upholds the invariant. And finally, the third component is consumption, and this is where we actually get our bang for our buck. We write code which consumes the safety invariant as a precondition, and it's only correct. The code that we write is only correct in virtue of the fact that that safety precondition actually holds. So in the case of a binary tree, our code is able to find the correct location in the tree of any node, or excuse me, any value in log n time, despite the fact that there are many other values in the tree that it's never touching. That optimization is only valid because we know that the tree is ordered, and we only know that the tree is ordered because we structured the rest of our code to define and enforce these invariants in the way that we have. So let's get into our first example, which is thread safety. What I'm going to demonstrate with this example is that not only can libraries use the language's core features to build new guarantees, but actually that the standard library itself already uses this technique, and you just might not realize it. In fact, the thread safety that Rust advertises on its website is nowhere in the language. It's only in the standard library. There is no reason, in principle, that thread safety in Rust could not have been built as a crate on crates.io. It's just convenient to have it in the language, or excuse me, in the library. So let's imagine that you're writing spawn. So spawn is a real function. This is from the thread module in the standard library. I've sort of stripped down the signature just to keep it simple. Now, if we think about how we might want to implement spawn, we immediately run into a limitation in the language. Because the language itself doesn't actually have any mechanism to interact with threads. Threads are an operating system concept, and so you have to go outside of the language to even interact with threads in any meaningful way. So for example, on a POSIX system, we might need to call libc pthread create, right? And this is where we run into our first core abstraction that we're going to want to use as a building block. Because libc functions like pthread create are implemented outside of the language, Rust has no visibility into their behavior. And so it can't guarantee that if you call pthread create, that won't violate one of Rust's safety guarantees. And this is why Rust introduces the notion of unsafe code. Unsafe code is code which Rust cannot guarantee will not violate its memory safety guarantees. Now, that doesn't mean that it definitely will. It just means that Rust isn't smart enough to rule it out. And so what we need instead is for Rust to rely on the programmer to do the heavy lifting. And that's where unsafe blocks come in. An unsafe block, like the one on this slide, gives the programmer free rein to perform any operation that Rust can't reason about. But in exchange, the programmer is swearing an oath of fealty that they are responsible for upholding memory safety themselves. And if they mess it up, all bets are off. And this is our first example of using a core abstraction to extend the power of the language. Rust, on its own, in the language definition, provides unsafe functions and unsafe blocks, but it doesn't provide any mechanism for interacting with threads. However, by using unsafe in combination with external APIs like pthread create, we can teach the language about threads like we've done here. Now, as this is written, this implementation is unsound. Not all values are thread safe, meaning not all values are sound to send between threads. So think of the distinction between arc and RC, for example. As written, there is nothing to stop you from passing a closure which captures some value which is not thread safe. So what the language does, or the standard library, is to encode the notion of thread safety in the type system. So first, we introduce a trait called send. This is the standard library send trait that you all know and love, right? Now, this is not a new thing. This is just the one that you're all familiar with. Note that this is an unsafe trait. Just like unsafe functions, unsafe traits tell the type system, this trait has safety implications that you're not smart enough to reason about. And so just like calling an unsafe function requires an unsafe block, implementing an unsafe trait requires an unsafe impl block. In the same way, the programmer has to opt into taking on the responsibility for upholding memory safety. Now, since the language can't reason about the meaning of send, it's just an opaque type with some name, an opaque trait, excuse me, with some name, we have to document its meaning in prose like we've done here. In this case, we say that a type can only be send if it's thread safe. And now that we've introduced that, we can use it as a bound elsewhere in our program. So in this case, spawn requires that the closure that you pass implements the send trait. Once we've done that, there's no longer a risk that a programmer could accidentally call spawn with a non-thread safe value, because if they did that, it just wouldn't type check, it wouldn't compile. So we've introduced this send trait that encodes the notion of thread safety, but we haven't actually implemented it for anything, so let's do that. So first we can implement it for any built-in type that we know off the bat is already thread safe. Now from Rust's perspective, this is just axiomatic. Using these unsafe impl blocks, we're just declaring by fiat that the send property holds of these types. Because Rust has no way of knowing what send actually means, it just sort of has to take our word for it. We can also implement send for more complex types. So for example, a mutex. Mutex is thread safe by design, and so it's okay to send mutex references between threads. And finally, we can permit arbitrary composite types to implement send by writing a custom derive. Now, obviously in reality, this isn't actually how it works. The standard library uses auto traits just to make things a little bit nicer. But my point in this slide is to reiterate that there's no reason in principle that send could not have just been developed as a library maintained by somebody other than the Rust project. Again, the core abstractions of the language on their own are enough to permit somebody to build an abstraction as powerful as send outside of the actual language project itself. So sticking with this hypothetical, our custom derive would automatically emit an unsafe impl block with the appropriate bounds. So in particular, a type can be send if all of its fields are send. So let's tie all of this together. Since send is just a normal trait, and we've written our impls, it works like any other trait. We know that this foo type, in this case, is send because, well, we derived send for foo, and we manually implemented send for mutex, and we manually implemented send for all the primitive types. So how does this example fit into the framework that I described before? Well, first, we define send, which teaches Rust about a new trait, and we use prose to document that send carries a special safety property that Rust can't reason about. Second, we enforce that safety property. We define send as an unsafe trait so that users can't violate the safety property without having to write the unsafe keyword. We manually implement send for types that we know are thread safe, and we provide a custom derive that does the same. Finally, in the spawn function, we use a send bound to justify that our internal call to pthread create is actually sound. And that's how Rust guarantees thread safety without any support from the language itself. So our second example is about deadlock prevention. This is work by Alex Conradi, who was on the netstack 3 team at the time, so I'm basically just bragging for him. So imagine that you're writing a netstack, and you want to make your stack multi-threaded. You care about performance, and so instead of just putting one big mutex around the whole thing, you use a lot of little tiny mutexes, right? Fine-grained locking, if you've heard the term. And as we saw in the previous example, Rust is going to guarantee that anything that we do with these mutexes is thread safe. But it won't prevent you from deadlocking. So for example, imagine that we have two different threads, A and B, that try to acquire these mutexes in different orders. So in this case, thread A acquires the IP mutex first, while thread B acquires the device mutex first. This is a classic deadlock scenario. If we're unlucky, thread A grabs the IP mutex, thread B grabs the device mutex, and now they're blocked on one another, so we have a deadlock. And you can conceptualize this as a graph of the locks that we might want to acquire. So all threads start out in this unlocked state, and they can take different paths through the graph in order to acquire different locks. In order to avoid the risk of deadlocking, we need to make sure that this graph is acyclic. But this set of edges forms a cycle. And so in order to prevent deadlocks, we would need to remove at least one of those two edges. Now, this might seem like a fairly trivial problem given this example, right? It's pretty obvious from this code that there's a deadlock risk. But netstack 3 has 77 different mutexes spread across its code base. And again, 192,000 lines of code. When you're working in that environment, keeping track of the order in which you're supposed to acquire those mutexes gets really hard really fast. And indeed, netstack 2, its predecessor, which is written in Go, has historically been plagued by deadlocks. And so the netstack 3 team decided they were going to try to prevent deadlocks statically at compile time. In order to do this, they needed a way of encoding this graph in the type system, that lock ordering graph, and a way of ensuring that code is only allowed to acquire locks in a way that is consistent with that order. So let's see how they did it. So the first step is to name each mutex. This is just a thin little wrapper around the standard library mutex type, but it adds an ID parameter that is used to identify different mutexes as distinct from one another. To show how this works, let's go back to our example from before. We can define one type per mutex and use these as a name to refer to each mutex. Now, these are just type level only, right? They have no actual runtime implication. Next, we define traits, lock after and lock before, that define the actual order of our graph. Now, they have to be unsafe, because a user could implement them and introduce a cycle, which would be invalid. Next, we define a macro for people who don't want to implement them manually and unsafely, and that implements the traits on behalf of the user. Now, let's zoom in on this blanket impl in the macro expansion. Don't worry about trying to follow the logic here, it's kind of convoluted, but the consequence of this blanket impl is very important. If a user invokes the macro in such a way that introduces a cycle into the graph, that will result in a blanket impl conflict, which means cyclic graphs will not be able to compile. So the next thing we need to do is introduce a lock context. And this keeps track of where we are in the lock graph at any given point in our source code. It's a zero-size type, so it has no cost at runtime. And using these building blocks, we can finally build a deadlock-proof locking API. So let's walk through the components of this type signature one by one. First, we require an existing context. Note that we borrow this context mutably, and what that does is it disables the context for further use until we've actually unlocked the mutex, right? So long as we're holding this mutex, that context is effectively unusable. Second, we require that the existing context that we're taking in has an ID which is upstream of ours in the lock graph, right? This is what prevents us from actually locking something that we've already locked. And finally, we return a new context that the caller can now use to continue locking mutexes, but it has the same ID as our lock. So it effectively prevents the user from doing anything that isn't downstream of our lock in the lock graph. And then, of course, once the mutex guard is dropped and you've unlocked, then you can go, everything sort of gets unshadowed, basically, and you can go back to using the things that are upstream of you. Finally, one little last bit of boilerplate. In order to represent the root of any lock graph, we have to introduce a sort of global, like, unlocked state, so anybody can construct this unlocked state. So let's go back to our example and see how we can use this new machinery to prevent deadlocks. So as we showed before, we introduced one type per mutex. And we use the macro to encode our graph in the type system as implementations of the lock after and lock before traits. Remember, this code only compiles if the graph is free of cycles. So let's walk through an example of how we can use this at runtime. So first, we construct a new context, which starts off in the unlocked state. And then we lock our first mutex, which is the IP mutex. Now this generates a new guard and a new context that we can use further on in the program. And finally, we repeat the same process for the device mutex. But now let's look at what happens if we try to introduce a deadlock opportunity. So as before, if we start off in the unlocked state, but now we directly lock the device mutex. Now this on its own is actually fine. We haven't introduced a cycle yet, so this actually compiles. But because we've acquired the device mutex, and now that context object that we have is linked to the device mutex, if we try to acquire the IP mutex, this will not compile. Right? Because the point is that there's no edge in the graph from the device mutex to the IP mutex. So this will be a compilation error. So let's talk about how this fits into the framework that we've been talking about. First, again, definition. We define the lock after and lock before traits, and we document in prose that they carry a safety property, in this case that they are acyclic. Second, we define the mutex type, and we document in prose that it carries a safety property, namely that it's only allowed to be locked consistent with some existing lock ordering graph. Next is enforcement. We make these traits unsafe so that a user is only able to violate the cyclicality property if they actually, swear fealty. We design our macro so that it guarantees that only acyclic graphs are able to compile. And we use a lock before bound to ensure that you're only able to call the lock method in a way that's consistent with the pre-existing graph. And finally is consumption. The lock method itself uses the lock before bound to justify that the internal call to the mutex lock, right, just the standard library mutex, isn't going to deadlock. Now, I should note that what I've presented here is a simplified version of what exists in practice, and you can go see the real code if you look at my references. There are actually two subtle ways that I'm aware of in this example that you could actually violate deadlock safety. And there's an interesting conversation to be had about whether safety properties like these should be literally impossible to circumvent or just like hard enough that it's hard to shoot yourself in the foot by accident. And actually, the real example of this code doesn't try to go this hard, and it just says, like, look, it's hard to do this by accident, and don't be an idiot, basically. It's the distinction, the sort of debate between those two perspectives is like completely orthogonal to this talk, so I'm not really going to get into it. So how has this played out for netstack 3? Well, in the beginning, netstack 3 was entirely single-threaded for simplicity. But over the past few years, the team has been working to thread mutexes and mutex guards through the entire netstack. Again, there's 77 of them, so it took a while. And finally, literally a few weeks ago in mid-August, they had finished the process of adding mutexes everywhere, and they were finally ready to flip the switch, to go from running on one thread to running on multiple threads. And so they changed the default number of threads from 1 to 4, and that's it. That's the code. It was done, bug-free, landed, done. Okay, so those are my two examples, and I want to encourage all of you to try this methodology out for yourselves. I would especially encourage you to bring it to new domains and new classes of bugs that nobody in the Rust community has tackled yet. So I'm going to give a few concrete pieces of advice to help you get started down that road. One, think of your functions as, think of partial functions in your API as a code smell. Your public functions should never panic, and they shouldn't return option or result unless that's actually part of the behavior that they're modeling. So returning an error because an I/O operation failed is unavoidable and totally fine, but returning an error because the caller passed an invalid value, that shouldn't have compiled in the first place. For great primers, I'd recommend these 2 blog posts. Make your APIs exactly match the structure of the problem that you're modeling. This is the error type that's returned when netstack 3 fails to parse an IP packet. Now, this might seem surprisingly convoluted, but this is a faithful representation of the complexity of both the IPv4 and IPv6 protocols. To do anything simpler would cause problems for us down the line. For example, if we zoom in on the parameter problem pointer field, we can see that part of the spec is that if you receive a malformed packet, you're supposed to respond to that packet with an error message that provides a pointer into the original packet where the problem was encountered. Note the generic type here. In IPv4, the field in the error message that you are supposed to send is 1 byte long, while in IPv6, it is 4 bytes long. And if we didn't use generics here and we just said, we're always going to use a U32 or something like that, then what we would do is we would have to introduce a fallible conversion somewhere else in our code base that, if we had a bug, would either silently produce incorrect packets or would crash the stack because it would panic. But by doing this instead, by faithfully encoding in the actual type itself the exact semantics of the protocol, there's no way for us to actually have that bug. Also, don't expect that the solution is going to be the same every time. Just because the catchphrase is always that buggy programs don't compile doesn't mean that there's a recipe. In my experience, different problems call for wildly different solutions that leverage a hodgepodge of different language features. And don't expect it to always fall out naturally. One of my favorite quotes is from Rob Pike talking about Go's design. Simplicity is the art of hiding complexity. Your responsibility is to do the hard work so that your users have a simple model of your API and they don't have to understand how awful the internals of your library are. I'm going to skip this one for time. Okay, finally, if you'll permit me a little bit of speculation, I think that this methodology has the potential to fundamentally reshape how we engage in the process of software engineering. And I think that so far we've only scratched the surface. One reason is that there are domains where correctness is a much bigger deal than it is for most of us in this room, right? Rust is only just starting to make inroads into high assurance domains like automotive, aerospace, medical devices, and so on. And another is that this methodology allows software to scale much more effectively, and we certainly saw that with netstack 3. So, as I mentioned at the beginning, I wasn't able to provide nearly as many examples as I would have liked to, and I really encourage you to check out these references. Talk to me about any of this stuff in person on Discord, et cetera, et cetera. I really believe that thanks to Rust, we have the opportunity to fundamentally improve the state of software engineering, and I intend to spend the next phase of my career proving it, and I hope you'll join me. Thank you.